SpaceX just shocked everyone with their Mars landing plan. When Starship reaches 100 meters above the Martian surface, it'll tip from vertical to a 30-degree angle in just 10 seconds, then land horizontally on a deployed composite pad. Why would they do something this radical? The answer lies in basic physics. Landing on legs creates 4 kilograms of pressure per square centimeter, enough to sink deep into Martian soil. But spreading that same weight across 160 meters horizontally? Just 0.3 kilograms per square centimeter. Let's dive right in. Now here's what most people don't understand about Mars. Everyone thinks returning to Earth is the ultimate test for Starship because our atmosphere is 100 times thicker, so it must be way more violent, right? Actually, it's Mars that tries to murder your spacecraft. When Starship returns from low Earth orbit, it's moving at 7.8 kilometers per second. It slams into that thick atmosphere, plasma erupts everywhere, temperatures spike like crazy. But here's the thing, it's over fast. 4 to 6 minutes later, most of your speed is gone. Mars doesn't give you that mercy. A Starship headed there from interplanetary space screams in at 11 to 12 kilometers per second, almost 50% faster than Earth reentry. But the atmosphere is so pathetically thin, it barely slows you down. So what happens? Instead of a short, violent burn lasting minutes, you're trapped inside a glowing plasma bubble for 12 to 15 straight minutes. Same hellfire, except it just keeps going and going. Can you see why that's a nightmare for engineers? The math tells the brutal story. More speed plus longer heating plus thinner air equals an absolutely massive heat load. Peak temperatures climb to 2,500 to 2,700 degrees Celsius. That's up to 1,000 degrees hotter than returning to Earth. The Earth orbit version of Starship uses heat tiles optimized for quick turnarounds and reuse. The Mars version will need something far more advanced, basically a shield built to survive extended torture. But SpaceX isn't going into this blind. They're methodically gathering data right now through their test flights here on Earth. Flight 10 and Flight 11 weren't just about catching Starship with Mechazilla. That's only part of the story. In those missions, SpaceX slowed down a spacecraft weighing over 100 tons from several thousand kilometers per hour to just 1 meter per second before ocean splashdown, using only 1 or 2 Raptor engines. Think about what that data represents. They're capturing real-world information about heat shield performance, engine relight sequences, and the belly flop maneuver, all critical steps for Mars. Once they have this raw data, AI can simulate it under Martian conditions. How valuable is this approach? Look at NASA's Curiosity rover for context. Before that famous sky crane landing on August 6, 2012, NASA went absolutely wild with testing. They dropped a full sky crane system with the rover from a helicopter. They released the rover from a balloon 500 meters above the Nevada desert. They simulated the entire 7 minutes of terror, literally thousands of times, both in software and with real hardware. When the real mission happened, the landing was nearly flawless. The control room went dead silent, then exploded with joy because they couldn't believe they'd actually pulled off something that insane. SpaceX is following the same playbook, just scaled up massively. Here's where it gets really interesting. Even if Starship survives that brutal 15-minute plasma bath, it still faces the final exam, the actual touchdown. And this is where the horizontal landing concept becomes brilliant. On Earth, Starship can land on Mechazilla or splash down in the ocean. Mars offers no such luxury. No tower, no ships, no soft water landing. Just rugged, rock-covered terrain that's completely unforgiving. Traditional thinking says you land vertically on legs, just like the Apollo missions or the planned Starship HLS for the moon. And yes, the HLS version already has landing legs. 6 hydraulic folding legs designed for lunar gravity. But here's the critical difference most people miss. The moon's gravity is 1/6 of Earth's. Mars has nearly 3 times the lunar gravity at 0.38 g. That changes absolutely everything. Take a 250-ton Starship landing on the moon. Each of those 6 legs only handles about 70 tons of force. The lunar soil is dry, compact, and the weak gravity forgives a lot of imperfections. Even if you touch down a few meters off target, Those wide ski-like pads keep you stable. Now drop that same 250-ton vehicle onto Mars. The load on each leg instantly jumps to around 155 tons, more than double. The surface is harder, rougher, and far less forgiving. What does this force you to do? The legs can't just be scaled-up versions of HLS. They have to be 2 to 3 times thicker and significantly heavier to spread out the load and prevent the ship from tipping the moment it touches down. More weight means more fuel needed, which means less cargo capacity. Worse yet, those legs create pressure points of 4 kilograms per square centimeter against the Martian surface. In softer areas, that's enough to sink the landing pads deep into the soil, potentially destabilizing the entire 50-meter-tall rocket. One bad touchdown angle and you've got a $2 billion vehicle tipping over 140 million miles from the nearest repair shop. Is this really the best we can do? That's exactly the question SpaceX engineers asked themselves, and their answer flipped the entire concept sideways, literally. Picture this. Starship approaches the Martian surface vertically, just like we've seen in test flights. It uses all its engines to slow from 1.6 kilometers per second down to just 2 or 3 meters per second. At about 100 meters altitude, the RCS system, a network of 48 small thrusters distributed across the spacecraft, starts firing. Over 10 seconds, these thrusters gradually tip Starship from a 90-degree vertical stance down to roughly 30 degrees. Then it gently sets down on a 50-centimeter thick composite landing pad that deploys from the belly of the ship. The physics are elegant. By spreading the contact area across roughly 160 meters instead of concentrating it on 6 small landing pads, the pressure drops to just 0.3 kilograms per square centimeter. That's more than 13 times lower than vertical landing. Think of walking on sand. Distribute your weight across snowshoes and you barely leave a mark. Put all that weight on high heels and you sink straight through. Same principle, just with a 250-ton spacecraft. But the advantages go far beyond just lower ground pressure. For astronauts, this design is infinitely more practical. They exit via a 3-meter ladder instead of a 30-meter elevator system from earlier vertical concepts. A horizontal Starship immediately becomes a Mars base. That 1,000 cubic meter interior provides instant living space. The exterior can be covered with a layer of Martian regolith, blocking up to 80% of cosmic radiation without building separate structures. Side cargo bays allow 2.5-ton rovers to roll straight out. No cranes, no complex elevator systems, no additional infrastructure needed. Here's what really makes this approach game-changing. When you're planning not just one landing, but dozens or even hundreds, efficiency becomes everything. Elon Musk recently said it needs to be sustainably multiplanetary, not just visiting, but actually multiplanetary in the sense that you have planetary redundancy. Within the next 5 years, we'll likely see at least 5 Starship launch pads across Florida and Texas. That rapid expansion tells you everything about the scale of ambition here. We're not talking about planting a flag and leaving footprints. We're talking about sending millions of tons of cargo to Mars, enough to support a fully independent, self-sustaining society. This isn't some distant science fiction dream. The horizontal landing method solves real engineering problems that would otherwise make Mars colonization nearly impossible. Lower ground pressure means stable landings on unpredictable terrain. Instant base functionality means crews survive from day one. Direct rover deployment means exploration starts immediately. Here's what's most remarkable. While other space agencies plan single Mars missions decades away, SpaceX is already stress testing the technology right now. Those belly flop maneuvers during test flights? That's Mars landing practice under Earth's thicker atmosphere. The heat shield data they're collecting? It's being fed into AI simulations for Martian reentry. Every flight brings us closer to the moment when Starship tips sideways and settles onto Mars for the first time. The question isn't whether this will work. The physics check out completely. The real question is how soon. Given SpaceX's current pace, we might witness the first sideways Mars landing before 2030. That's just 5 years away. What do you think? Does laying Starship down sideways seem crazy or brilliant? Drop your thoughts below. And if you want to stay updated on every major SpaceX development, subscribe to Space Update 24 Hours and turn on notifications. This journey to Mars is accelerating faster than anyone expected. You won't want to miss what happens next.